Hi and welcome back to another LeetCode video. Today we're looking at LeetCode 139, word break. It's a medium problem and it's a classic dynamic programming problem, a one-dimensional, mind you. And I'm going to show you two different ways of how to solve this. One is going to involve a standard string matching algorithm and the other one is going to involve a try, which will significantly speed up things and which should be extremely exciting for us. So let's just understand what this problem is about, and then we'll dive into the two different implementations. So we're given a string S and a dictionary of words, and we should return true if we can segment that string into words from the dictionary. Here's a nice example. So we have the string LeetCode, and we have the dictionary of words that contain the word lead and the word code. Obviously, you can split the string into lead and code. So in that case, we have to return true. The next example is one that demonstrates that we can actually reuse a word from the dictionary multiple times, right? So here we have the string apple, pen, apple, and our word dictionary contains the words apple and pen. So the answer is true. Yes, we can segment that string into words that are in our dictionary. Now, the third example is a negative one where we have the string cats and dog, except that and dog there's only one D here, which they both use. Now in our word dictionary, we have the terms cats, dog, sand, and cat. And we're not able to build a match here simply because even if we match cat first, and cat is a word in the dictionary, then sand, which is, we can segment cats and into cat, sand, or cats and. But we are left with the two characters OG, which is the postfix of dog. But since we've already consumed the dog from and, there's no way that we can finish the match. So the output here is going to be false. We were not able to segment the string S into words from the dictionary in this case. Well, so since this is a dynamic programming problem, the first question you should ask yourself, well, if you know that's a dynamic programming problem anyways, first question that you should ask yourself is, what are the overlapping subproblems here? How can we build the solution by building, solution up from maybe some small building blocks? And whenever it's like a string matching thing or something, your mind should immediately go to, can I segment, let's say, just the postfix of the string into words that are in the dictionary? And this is exactly the idea that we're going to use. So we're going to try to match the string or the postfix E. Can we segment that? No, we can't. Can we segment the postfix DE? No, we can't. ODE? No. But code we can. Yes, very good. So, and then we know, okay, for this postfix of the string, we have a segmentation. So now we only need to check whether the remainder of the string has a valid segmentation. And by the way, just a comment. So you can do it from, you can approach it by iterating from the back of the string, but you can also approach it by just, doing it greedy way right away. So you could say, okay, can I match L? Is L a valid word in my string? Is LE, LEE, LEET one? Yes, it is. Fantastic. So now we just have to check the remainder of the string if we can also segment that. And actually, yeah, I think I'm going to implement the solution where we start from the beginning. So if you've done a couple of dynamic programming problems, implementing them recursively should be natural to you. And I'm just going to show you how I would do it. So I would have a little helper function. Let's just call it def first search helper. And that should tell us whether from string at position I, do we have a valid segmentation? Well, obviously we're going to if we want to start from the start, we just pass an index 0, and then we expect this function to return us, does there exist a valid segmentation of our string from index 0? Well, now what we need to do is, we will have a base case, right? That will terminate the recursion, and that occurs when I is basically out of bounds, where we say if I is larger than length of the string S, or length larger or equal, then we're just going to return true by default. because we're going to assume that, you know, the empty string, we can match it by just not picking a word from the dictionary. So yeah, in that case, we just return true. Now, for when we don't hit the base case, we basically now have to test whether any of the words in our word dictionary are a prefix to our string starting at position I. So that's exactly what we're going to test. So we're going to iterate over all of the words, word in, word dict, right? And now we need to check if, you know, if S from position I starts with the word. Now, this expression creates a copy of the string, right? And so this we want to optimize this here in a second. But bear with me for a moment. So if that is the case, well, that is fantastic. So we found one possible prefix of the string, and maybe in example 3 that could be oh, nice. We matched cat, sorry. We matched cat, right? Fantastic. So now we just have to check whether sand, dog is also segmentable. Oh, and the way to determine that is just by calling the recursive helper function at position I plus the length of the word that we just matched, right? And if that returns true, we also need to return true. Now, if it returns false, that means we have to continue iterating over the words in our dictionary and try the other ones, you know, whether they have a match. Only when we've exhausted all of the possible words and we didn't find a match, then we know for sure that we're not going to find a match from position I, well, we're not going to find a valid segmentation from position I for the remainder of the string S. Right, so now let's talk about, well, yeah, let's talk about optimization. So with dynamic programming, you always have a component where you have some kind of memory that you use. And if you look at this, you should immediately see that we're going to try a bunch of different indices to compute from. And it's quite possible that when you have a scenario, let's say we have the string contains only of A, B, A, B, A, B, and you have a word dictionary that contains A as a word, contains AB as a word, and that contains the word B as a word, right? That means one possible match for, let's say, the first 4 characters would be you match A, you match B, you match or you match AB directly. Now, they both will end up at index 2, right? And we found different paths, but it also means we're going to call our default helper function with the same parameter for each of these 2 different paths. But we don't want to recompute the result. And what we're going to do is we're going to remember what we computed, you know. We computed whether from index I, we can segment the remainder of the string. So we don't want to compute that again, and we just cache the result. And in Python, you can just use the cache decorator, which creates a hash map that stores the result of calling this helper function with this parameter. And once that result is stored, whenever you call this function again with that parameter, it will just return the stored result instead of executing the code of the function. You can also do this manually by just saying, okay, you have a cache dictionary, and then you check if I in cache, then you return cache I. That's exactly the same thing, and at the end you also have to, you have to update the cache yourself, and when you return true, you first have to write true back into your cache, etc. But Python gives us this ability to use this one-liner, this annotation, or this decorator to give us this functionality out of the box. So that's what we're going to use here, but it also means we're going to have some space complexity that we just added here. Right, so that is how we can basically find a match. And so this should already work. And it does. Now let's get rid of the string copying here. Well, we want to implement our own little starts with function, right? Our prefix match function. We're going to well, give it an index and a word, and we're going to check whether the string s from position I starts with all the letters of word. We have to take care of an edge case. If I plus the length of the word is larger than the length of the string s, well, it can't be matched, so we just return false. Now, if there is a possible match, well, we have to check it. So for j, we iterate over all of the characters in our word here, in range word, and then we just do the comparison. If string at position I plus j, I is kind of our offset, is not equal to the word at position j, well, then it's a mismatch, right? So we return false in that case. Only when we've iterated over all of the characters and we didn't find a mismatch, we can return true, because that means string s from position I continues with the word, with the characters and words. So we'll just replace this with our word, and we just pass an I. And now we don't copy the string anymore, but we still have an O of n comparison in the worst case. So let's run this now. And it passes as well. I'm just going to submit this to see if it passes all of the tests. Nice, and it does, you know, and you could also add some extra caching here if you wanted to. Well, actually, I don't think we need to do that here. Yeah, we don't need to do that here. Excuse me. All right, and well, now let's talk about space and time complexity for this approach. So obviously, well, our runtime complexity depends on how often do we have to call the helper function. In the worst case, we have to call it for every position I of our index. Say our string consists only of the letter A, something like this. And we have a lot of characters or a lot of words in our dictionary, and maybe they're all, I don't know, some weird ones. But A comes at the very end, and when we iterate over the word list, we actually first have to iterate over all of the possible matches. That would make things not more complicated, but would take more time. So this would be a worst case scenario. So what we have, well, I guess we have the length of the string s, right? What else do we have? We have the length of our word dictionary. Maybe call this M. Sorry, M. And we also have the K, which is the maximum length of any word, right? Those are the three things that we're going to need. And when we talk about the runtime complexity, well, what do we actually have to do? Well, we have to iterate over all of the characters in our word, so that's going to be O of n, times all of the words in our dictionary, which is going to be M, so O of n, M. And every time we have to do a string comparison. We have to call our starts with method, which gives us O of times K, right? You could also pick K as the average word length, but no, actually you have to use the max one, yeah. So yeah, so that would be our runtime complexity and time. And what about space? Well, space, we're going to store at most n values for the cache, right? It's going to be n, because I can only assume values between 0 and n. And what else do we have to? Well, we have to do with stack space, but stack space is never going to be larger than n, right? Can't have more recursive calls than we have different ways of calling the recursive helper function. So yeah, so that would be, one more second. Did I get that right? Yes, I think that is correct. Yeah, so that would be our space and time complexity analysis. And yeah, well, I promise you another solution with an implementation of a trie. I think I will break that into another video. So the next video should be about how to do this with a try, bring down, well, the time complexity mostly.